Hey there, chemistry. This is Mystery Arc. This is vodcast 8.4, where we're going to be talking about solubility and how temperature affects solubility. All right. So, if we were to increase the temperature of a solvent, what is it going to do? Well, what happens when you increase the temperature of anything? Well, if you increase the temperature of something, it makes those molecules move faster, right? So it's going to speed up the particle movement. Okay, it's going to make them move faster. And if it speeds them up, what's going to happen? Well, it's going to cause the solvent particles to bump into or collide into, so bump into the solute molecules. Okay, and when it bumps into the solute, what's going to happen? Well, the solute particles are going to break loose. And when they break loose, they end up dissolving, and they dissolve at a faster pace. Okay? So what would be some other ways that we could get a solvent to bump into the solutes more often? Right? Could we get something to dissolve at a faster pace? Well, what if we were to make more solute? Okay. Now, don't actually add more solute in there, but if we were to crush it or grind it, okay, what happens there? Well, we're actually increasing the surface area. We're going to make the surface area more. We're going to take that same amount that we had and crush it up so that we have more of it to bump into the solvent. Okay, what's another way? When you make your sweet tea or when you make your Kool-Aid, do you just pour the stuff in there and let it sit, or do you stir it? Oh, you stir it, don't you? If you stir it, what are you doing? You're agitating it. And when you agitate it, you're making those particles bump into each other. Oh, so these are all things that can help increase the rate at which the solubility happens. Okay, so if you increase the temperature, you increase the agitation or you stir it, and if you crush it up and make the particles smaller, that gives it more surface area, then you'll end up dissolving things faster. All right, well, what happens when we dissolve things in liquids? Well, as we dissolve something solid in a liquid, what's going to happen as the temperature goes up, the solubility of that substance will go up. Okay, think about this when you make your iced tea. Okay, when you make iced tea, can you put a lot of sugar in it when it's cold? Probably not. Okay, when's the best time to add your tea or to add your sugar? When it's warm. Why? Because the particles are moving faster and they're going to collide with each other more, and it's going to dissolve faster. Right? So solids will dissolve in liquids at a quicker rate, which gives us this nice linear line with a positive slope. Okay, well, gases, right? Think about your sodas. Okay, what happens when you pop the top on your soda can? When you pop the top on your soda can, you usually hear a psh, right? What is that noise? Well, that noise is the gases that have been forced to go into solution. They're escaping. They're getting out. They don't want to be in solution, right? Okay, and think about it. What happens when you have a hot soda versus a cold soda, right? The hot soda, you're going to hear that it's going to go flatter quicker, right? We say it's flat when it doesn't have any carbonation in it, right? And that's because the hotter the substance is, the less those gas molecules want to stay in solution. Why? Because they're moving. They're like, I'm out of here, buddy. I'm not hanging out. And so our slope here, as the temperature goes up, the solubility of a gas goes down, and it has a negative slope. All right. Okay. Oh, I left something off on here. Let's talk about this. All right. So just to wrap this up, solids are more soluble at higher temperatures as you increase the temperature. Right? What about gases? Well, gases are the absolute opposite, right? They are going to be less soluble at higher temperatures. Okay? So if you want to dissolve something that's a gas, you want to make sure that you lower that temperature. And you also want to make sure that you increase the pressure so that you can get that gas to go into the liquid state. Okay, a solubility curve. So we talk about solubility, and we like to, in science and in math sometimes too, but in science we like to show a lot of graphics. We like to show a lot of graphs and visuals so that you can see what we're talking about and understand what we're talking about, not just with the words that we're saying and the words that you're reading, but with our graphs. Okay, so we use this thing called a solubility curve. And a solubility curve is essentially, it's a graph. Yay, we love graphs. No, we actually do. They're really cool. All right, lots of information, little bit of reading. That's why we like them so much. Yes, little reading. Okay, so a graph of the solubility of a compound, and it shows it at various temperatures. Each compound is going to have a different solubility curve. Okay, it just depends on the compound. And guess what, guys? Solubility is dependent on, oh, we've been talking about this whole time, temperature. Right, temperature. Okay, so what does a solubility curve look like? Well, you've got one on your paper there. This is what it looks like. Okay, so let's look over the solubility curve, and we notice that it's got tons of lines. There's solid lines, there's dashed lines, they're all over the place, right? And it says solubility in grams of solvent for 100 grams of water. So what are the trends that we see on the graph here, right? When you're looking at this, what do you see that's a trend? Well, I don't know about you guys, but I noticed that these dotted lines, there's 3 dotted lines on here, and every single one of the dashed lines or the dashes or the dotted lines have negative slopes. Right? They're all going down. And the solid lines, well, this one's not really going up too much, but it's still going up, right? So all the solid ones have positive slopes. Okay, well, let's look at that. The dashes all stand for gases, and gases, we said, have negative slopes. Huh, that must be true. All right, and then we also said that the solids have positive slopes, right? As you increase the temperature, they get more soluble. As you increase the temperature, these get less soluble. Okay? So how do the solubility of gases and solids differ? Well, as temperature increases, gases less soluble, and solids more soluble. But you guys already knew that. I know. All right, so if you stir faster, will that make you dissolve more? All right, now we talked about this. We said if you stir it, it'll dissolve faster, but will it dissolve more? No, it will not. All right, so why not? The reason it does not dissolve more is because you're just increasing the number of collisions it's having. You're not adding more stuff to it. It's not going to make it dissolve more. The only way you can get it to dissolve more is by increasing the temperature. So you need to increase the temperature in order to get it to dissolve more, and that's how you end up making your super saturated solutions. Okay, so we've got a couple different terms that we can use to talk about these solutions. We've said these before. We've got a saturated, we've got unsaturated, and we've got supersaturated. Okay, those 3 supersaturated. All right, so those 3 will be used to determine or to define a solution. So how do we use this graph over here? We're going to use these 3 words to answer these 3 questions. It says what term, saturated, unsaturated, or supersaturated, describes 39 grams of sodium chloride at 70 degrees Celsius. All right, so we have grams here and we have degrees temperature. It didn't say it, but this is temperature here in degrees Celsius. Okay, so we find 70 degrees Celsius, which is here, and we go up until we get to 39. And 39 would be about right here. All right, and the question is, how would you describe that? Well, it's not... we would say that because it's above the line, that would be a saturated solution. All right, it's above the line. If it was on the line, it would definitely be a saturated solution. But if it's above the line, it's going to be saturated because we don't know if it's really been heated enough to dissolve everything that's left over. Okay. All right, so then we look and we say at 30 grams at the same temperature. And so we would come here and we would say, well, what is that? Well, we're still looking NaCl, which just so happens to be the blue line, and it's below. So we would say that is an unsaturated solution. Okay, same temperature, and they want to know about 45 grams. So if we come all the way up here, it's still going to be saturated. Now we could say that it could be a supersaturated solution, but we're not sure though, right? So we'll put super here because in order for it to be a supersaturated solution, it would have to be heated and allow that excess solute to dissolve. Okay? And if I can, I'll show you what it looks like, a supersaturated solution. Okay, Each substance, so for characteristics of substances, each substance has a different maximum amount of solute that will dissolve, and that's what we call its molar solubility. Okay. Curves for gases have negative slopes, and curves for solids have a positive slope. So all we're doing is recapping what we just said on that same one. You've probably heard that like 4 times. It's probably important. Okay. All right, so what's the difference between an unsaturated solution and a saturated solution or supersaturated solution? So an unsaturated solution is one that contains less dissolved solute than the solvent can normally hold at that temperature. Anywhere below that line, it's anywhere below the line of saturation. So if I had a graph here and this was my line of saturation, anything down here would be considered unsaturated. Okay, supersaturated solution is a solution that contains more solute than can actually be dissolved at that temperature, and anywhere above the line could be considered a supersaturated solution. We just don't know if it's been heated all the way up enough. Okay. All right, so how do we use this solubility line or solubility curve to answer questions? Well, we've already showed you a little, but let's go through another couple more examples. So here it says at 45 degrees Celsius, how much potassium nitrate will dissolve in 100 grams of water to form a saturated solution? Okay, so we've got to find our potassium nitrate curve, which just so happens to be this one. Let's see if I can get a, let's put another color on it. Okay. This is my potassium nitrate curve, and this is the line that we're going to be using, I think, for all of these, but I'm not sure. Okay, so this potassium nitrate curve at 45 degrees Celsius, which just so happens to be here, how much will dissolve in 100 grams of water to form a saturated solution? So look, in order to make a saturated solution in 100 grams of water, or 100 grams of water, they want to know how much can we dissolve. So we go from here up until we get to that line. And when we get to that line, that's when we stop. And we say, when we're on that line, it's a saturated solution. So then we would just kind of come over here and we would say, oh, look, it kind of looks like it's a little around the middle. So you could say at approximately 74 grams. Okay, if you wanted to say 75, that's fine. I can't tell you it's wrong. If you wanted to say 73, that's fine. If you said 79, it's wrong. Why? Because it's not up there at the line. Okay, Ms. Ruard. All right. On the next one, it says, if at 60 degrees Celsius, so now we're at 60, we put 80 grams of potassium nitrate in 100 grams of water. So we're going from 80 grams at 60 degrees Celsius in 100 grams of water, and we were looking at that potassium nitrate curve, right? And it says, what is the level of saturation for the solution? Well, it's underneath the line of saturation, so we would consider this unsaturated. Right? And then for our last question, it says how much sodium chloride is needed for a saturated solution at 75 degrees Celsius in 200 grams of water. So now we're at 75 degrees Celsius. Okay, and they want to know how much sodium chloride, so we go until we hit the line for sodium chloride, which just so happens to be here, and that would be 40 grams. But that's 40 grams for 100 grams of water. They want to know 200 grams of water. So if I need to double this, and it becomes 200 grams, what do you think I have to do with this? Well, if you said double it, you're right. There you go. Okay, so 80 grams of sodium chloride in a 200 grams sample of water. Okay, that's it. I tell you what, hold on 1 second. I'll see if I can find a supersaturated solution for you. Okay, I don't think I'm going to have time, so when you guys get to class, just remind me and I'll try to show it to you then. All right, I'll see you then.